Hello, thanks for coming. I'm David Ledger. I'm going to be talking about standard function ref, how to save some time, space, and a little bit of sanity. So first off, though, just a bit of an introduction and a disclaimer. I'm here on behalf of myself and not my employer. And that the implementations here that I use in this presentation for benchmarks and examples, they are from third-party implementations. We don't have this in a standard library implementation as of yet. So this presentation is based on the latest working draft, the first proposal for standard function ref, and the latest, and also some experience using tools very similar to standard function ref. It's a relatively common pattern. I'm going to be covering standard function ref, some background concepts, how it can be used, how not to use it, how to shoot yourself in the foot, how it can benefit your code and save on some costs. And I'm going to provide some benchmarks for compile time, for runtime, and show you how you can save on some code space. So first off, what is it? Well, the proposals call it this. The first called it a non-owning reference to a callable. Latest called it a type-erased callable reference. I like just merging those two, a type-erased non-owning reference to a callable. I'm going to be basically referring to it like that for the rest of the talk. But it's a function wrapper, and we have lots of these. We have standard function, which is an owning function wrapper. It owns the data, it stores it, it copies it every time. But it requires runtime type information, and the callables need to be copyable. We've got move-only function, lifts some of those restrictions, doesn't require that runtime type information, but it's also owning, and it adds expressivity. You can now express in these function wrappers exception specifications. We're going to get copyable function too. This one is also owning. I'm going over these ones very quickly because I want to get to standard function ref because that's much cooler. Copyable function is very much like standard function, only it lifts the need for runtime type information and it improves the expressivity of the interfaces. And now we're getting standard function ref. In C++26, we're getting the first non-owning function wrapper. It's a reference. It has reference semantics. And like the others, it is expressive, more so than standard function. I've made this table just for reference. These are kind of some of the qualities of these different function wrappers. You can look at these in the slides later. I'm not going to go over it all. It's two new types and an inline variable. We will get a type in the utility header, non-type, and standard function ref in the functional header. The non-type in the utility header is used to pass a non-type template parameter into some of the constructors of function ref. Function ref is just one of these specializations here. It's trivially copyable, which gives it some great performance characteristics. This has advantages, being able to pass through registers in some APIs, and it produces very small and fast code. It is the size of 2 pointers, which is really fantastic. It wasn't going to be at some points. So, before we really get into it, let's give some background. First off, what is a callable? What even are we wrapping? Because standard function ref could have been called standard callable ref if we had started with that sort of language to begin with. A callable is anything that can be called with standard invoke, and they are everywhere. We have 86% of the algorithm header. The overload sets within the algorithm header are providing overloads with callables. So we have them everywhere. So if you can improve your usage of callables, you can improve it broadly. They are function pointers and function references, both of which can be called with invoke. So they are callables. They are objects with overloaded call operators, and we have quite a few of these in the standard library. And this is a callable. We can use it with standard invoke, so it is a callable. Lambdas notably are basically syntactic sugar for this case. This lambda will transform into this. So both of these can be used with a standard invoke, so they are also callable. Member function pointers are also callable. You can use this as standard invoke, notably that you have to pass this additional object parameter in. I should use my mouse for that, actually. You can add that object parameter, so they are callable as well. Data member pointers is probably a more surprising case. These are also callables. You can use this with standard invoke, and haven't we all forgotten the syntax about how to access a data member pointer or a member function pointer? Probably several times. Well, shortcut, we can use invoke for that. Yeah. So a bit more background. What is ownership? Because standard function ref is non-owning. Well, it doesn't store the callable. It stores just a reference to it. And it is more like string view than it is string. String view has many problems, and standard function ref has those same problems. So with that, let's go into how to use it. So if you want to use standard function ref, we can use it very similarly to how we would use standard function. We can just pass it a function pointer, and we can construct it. We can alternatively use this non-type template parameter to construct even with free functions. In this case, we may get some performance benefits because the function pointer here gets embedded in something called the func, and we'll talk about what that is later, but this may have some benefits. I haven't seen them, but it may happen. You can also construct with a lambda or a callable object. If you have an object that has the overloaded call operator, this is equivalent. Just pass them in as a reference, and you can get your standard function reference. We can also use that with those member function pointers, and this is where it gets a little bit weird. This is where it gets away from what we're probably used to. We have to pass in the member function pointer using that non-type template parameter of non-type. It's the first argument, and it doesn't have to be a member function pointer. It could, in fact, be, which I'll show later, something else. We can either bind the object along with the non-type template parameter member function pointer, or we can decide to omit that. But note here, the signature of that second function requires the object as the first argument. This might surprise people, but you can use this to access data members. So you can pass that data member pointer in that non-type template parameter, and then associate it with your object, and you can access your data member on call. You can also do this with the omission of that object, and as long as you pass in your object to the call, you can use it. Standard function ref is a callable, so you can use it with invoke, or you can just use it like a function, because it is callable. Now, this is where we get into the more interesting stuff, how not to use standard function ref, because there's a lot of ways you can shoot yourself in the foot. And we need to be really careful using standard function ref, because we are referencing something, and we need to pay attention to the lifetime of what we're referencing. We need to be sure that the thing we're referencing outlives the standard function ref that we are using. We can do this with scope. So if it's from the enclosing scope, you're probably going to have a dangling reference. So right here, if we have this function get plus, we are creating a dangling reference almost immediately. The returned function ref fn is a dangling reference. It's pointing to something that is out of scope. So calling fn would be undefined behavior. So I have a question. Feel free to yell it out. Feel free to be correct or not. But is there a bug here? No. That's right. What about here? Right, there's no bug here either. What about here? That's the same two sets of code. We have got, for example, two different pull requests on Git. We can see these two things as separate diffs. The pull request only shows one of those two, so we only get visibility of one of these at a time. So we've caused a bug, but nothing that we saw in our diff was a bug. The composition is a bug. What we've got here is a dangling reference again. We've constructed a lambda. We've constructed a lambda. The lambda's lifetime ends at the semicolon on these highlighted lines. And the identity function does the simplest thing it possibly could. It just returns the thing it was given. But by the time you can use it, the lambda it is referencing has been destroyed. Its lifetime has ended. So the call to that print is, again, undefined behavior. So when we compose these kinds of things, we end up with bugs. So be aware of this. And when you use standard function ref, try to use it as an L value. Try to use it in not pass it like this, but instead, uh-oh. Yeah, I may have lost a slide. OK, so try to use it as an L value. So if we stored our lambda as a local in main and pass that local into identity, we would have no problem at all. Make your code tolerant of these kinds of issues, because we live in a world that is using GitHub, using GitLab, using all these different tools, and they give you visibility on a slice at a time. And if you don't make your code have visibility of bugs, often your reviews won't pick them up. And tests may or may not pick this up either. You may get the sanitizer picking it up, I would hope, but we can be more kind. We should be kind to our reviewers. We should be kind to our future selves, because we are an expert when we write our code, but we are definitely not an expert 9 months down the track. Make it easy to write correct code. Standard function ref, string view. We've learnt with string view not to return a reference to a local string. Don't return a reference to a local lambda. The same rules apply. So with that out of the way, how does it work? How's standard function ref made? Well, it needs to reference two types of callables, an object or potentially a free function. So let's bind those into something called a bound entity. We're storing only one of these at a time. It's a reference to a single callable. So we've made it a union. Now, it needs two different things here, because you can't convert between ordinary pointers and function pointers and round trip that. So you need both. So we can store both types of pointers. Now, what do we do with those? Well, we introduced a new interesting word, a func. The func is just a function pointer. It takes that bound entity as the first argument. And because the func is specifically chosen, it knows exactly which bound entity to use. There's no branches. It just knows. And you're going to see this later when I go through the constructors. The func is also passed the arguments, and that's about it. This is the pattern. And this should be a bit familiar. Often we see APIs pass in a void pointer and a function with a void pointer argument. This is essentially what we're seeing, except also you can pass args. This is called the func with the call operator. So we have a call operator in standard function ref. It is a callable. It is passed to the bound entity along with the arguments. Those are forwarded. And that's about it for the call operator. The constructors can construct from free functions. We've shown how to do that. But this is how that constructor is made. We have to cast our function pointer. And this might seem a bit strange. Why wouldn't we just store the function pointer verbatim? We know the type of the function pointer, right? We have the function type in the signature of our function ref. The reason is because standard function ref allows convertible results. It allows convertible arguments. So we don't know the type. So we're converting it into our void pointer, void function pointer, store it in the bound entity, and then and now we have a pointer to our free function. We now need to make a func. That's that free function, which knows what to do with the bound entity. The func is going to take the bound entity. It knows, because we are in the constructor, the type of the free function. It can reinterpret cast that free function back to its original type and use invoke to invoke that free function. That's basically the free function case. We note that the return value is convertible here. We're using invoke R, so it doesn't need to return the exact type here. It just needs to be convertible. This might be useful if you have something like is_space or is_digit. These things return integers, I believe, but you may want a function ref with like a bool or something. So you can construct from a callable object. In this case, we're just going to store a pointer to our object. In this constructor, we know the type of our original object, so we can perform some type erasure. So we've got a pointer to our object. It was stored as a void pointer. Our func can cast back to the original type in the constructor as we know what that is. There's nothing, there's no guesswork here. Once we dereference that, we can just invoke it, and because it is a callable, we're going to call our object. I'm omitting some concepts here which would constrain this to basically prevent function references from constructing function references, which would almost always be a bug, but this is essentially how you construct from a callable object. That non-type template parameter constructor is a bit interesting. Our member function pointer is passed in as a non-type template parameter. And in our func, we can access that directly from that non-type template parameter and invoke it. We're not having to store the member function pointer. And this is important because these would make it more than 2 pointers large, which would make performance degrade. Once we've done that, we can pass in our object, which we can cast back to its original type using the same trick as before, pass in our arguments, and we have invoked our callable. You don't need to pass that object in, though. You can pass in the non-type template parameter without the object. And in this case, it's just embedding the non-type template parameter in the body of the func. We're not storing it. It's part of the func. It's part of the code. We're not using the bound entity here at all, and it's OK. So I've omitted some fiddly details here. The highly alert would notice that I've removed a fair bit of the concepts in the constructors. They're mainly to prevent things like that reference to a function reference, which could just keep happening, and a chain of dangling references may occur. So why would you use standard function ref? What would motivate you to use that over another pattern? Well, first, I'm going to talk about the cost of types, because there is one. We talk about types as if they're free, but they're not. If you have this function with just 2 template arguments, and we had 2 types in the whole world, C++ has lost all its types except O and N. In a large application, we'll end up having each of these. We'll end up with 4 definitions, each of them stamped out separately. And each of these definitions will have a different size. Does anyone want to guess which one of these is the largest definition in terms of code space? Last one, yes. Yes, the last one is the largest, doesn't work so well with registers. And notably, the first one, 2 pointers, which is quite similar to standard function ref, and one of the way, two integers, and one of the reasons that standard function ref works so well. Lambdas are special, though. Lambdas have a unique type per lambda. Each of these lambdas, despite having exactly the same tokens, has a different type. So if we were to call foo, each with these lambdas, we actually get two different foo definitions. They look the same, but you will get two different definitions. If you didn't want that, I mean, you could bring the lambdas out the front. Nice one, you've saved on some function definitions. Or you could use standard function ref. The advantage here is that now we can do different things in these lambdas, and we still only have one definition. We've saved on definitions here in a more general way. So I want to show you why this matters, because it becomes very significant. And to do that, I'm going to build a thing. I build calculators every time I build a thing to demonstrate a thing. I don't know why. Calculators are just great demos of things, I think. And I'm going to make a calculator out of some reusable parsing library. I'm going to use that for my compile time benchmark. I'm going to use it for code size benchmark, and I'm going to use it. So the calculator is just going to have ordinary call syntax. It's only going to export integers. It's not going to be good. And it's going to be built with this with a composition of these things called parsables, just a C++20 concept. A parsable is going to take a string view, return a string view. The returned string view is going to precede the parsed token, and that's it. A string view can be valid or invalid in this library. If the string view points to a null pointer, it's going to be considered invalid. So if it's default constructed, we're just going to call it an invalid string view. Now that's important because we want to be able to select a valid string view over an invalid string view, because a default constructed string view has a size of 0, and so does an empty string, but they are different. So we've got a function to help us there called less_size. We're going to utilize tuple's lexical comparison of its elements here, so you can do this in order to provide this, but that's basically it for our comparison. We're also going to do a very naive, greedy parsing. We're going to take each of our parsables, which is that concept from before, and call parse on each of them. We're going to store the results. With those helpers out of the way, our first parsable. We're going to remove a prefix of a string if it starts with the prefix. If it doesn't, we're going to return an invalid string. We're going to do the same with whitespace. Remove all the leading whitespace if there is some. If there isn't some, well, whatever, it's still valid. This is an optional whitespace. Now, our function calls are a sequence of these tokens. So we've got the identifier, open bracket, arguments, close bracket. So let's define that as a sequence. And what this is going to do is use tuple to store each of those parsables. We're going to apply each element of the tuple and parse each of them one by one. If every single one of those parsables parse successfully, then we'll return after all of those parsables. We'll return the string at the very end. If any of them failed, we'll return an invalid string. Comma is going to be composed with that sequence, SEQ. So we've got whitespace, prefix, whitespace. We're going to allow whitespaces in our commas. I'm not going to go into this too much. And here's our little greedy parser. It's not very good. There's less naive ways to do this. But essentially what we're going to do is parse all of our parsables using that parse all helper. And then we're going to find the shortest result. The reason we're finding the shortest is because that's the least number of remaining characters, which means it consumed the most. So, yeah. We need to actually parse our integers. So we're going to just make a concept for that. This could definitely be like is integral, but I, for some reason, felt like listing them, so I did. Our value parser is defined like that. We're going to use charconv to actually parse this, and if that was successful, if it wasn't an error, then we're going to call a callback with the resulting value, and return a string view that precedes the parsed value. Okay? And if it didn't parse, then we're going to return an invalid string. When we run that callback from our previous value parser, we're going to use this copy assigner. It's just going to call this callback and save the result into value. Now, this one's a bit dense. Sorry about that. This is for parsing the arguments. This is just I'm just going to call this a tuple parser, and it's going to parse one argument after another, separated by commas. It's going to use tuples apply, and then it's going to call the parse arg lambda once for each argument. Notably, the last argument does not have a comma parsed. If any of these arguments fail to parse, then it will return an invalid string. Our function calls, they are a sequence of tokens. Our functions have parentheses, arguments, close parentheses. So let's just use sequence. There's our arg parser. And our function call has an identifier at the front. We're going to allow white space after the identifier for some reason, and then we're going to parse our arguments. Here's where our callbacks start. So our callable will be called with the resulting value. Our return value will be from our callable will be provided with ret. So yeah. We're going to define our operations with our callable parser class here. Each of them will be basically identical. The benchmark is set up so that fn here can be swapped with standard function ref or standard function, or just be used as a raw template. And this is how the benchmark will be set up. So the result of that first lambda is provided to the second lambda, which prints the result. So, okay, that's the setup of this benchmark. We've got to actually use it before we do anything else. So that's what it does. But this is what it results in. So if you were to use standard function ref, you can see that the code size is significantly reduced. Note, without type erasure, we're stamping out definitions for each of our different functions. We've passed in lambdas to all of our callable parsers, so each of those callable parsers and their methods are stamped out. Standard function had a similar effect to standard function ref in its code size reduction, but it had its own overhead. It had a significant overhead in the type erasure. So it has a fixed amount. If you look at the blue regions between the standard function and standard function ref, they're actually very similar. It is significantly different in the cost of the type erasure. Okay. So that is the code size breakdown. But how does that scale? Because we've done that once, and really, we care about how it scales. Applications don't have 5 functions. So we're going to start scaling this. We're going to start increasing the size of our benchmark. We're going to benchmark it for code size, compile time, and runtime. And it's going to be done by extending that calculator before. I'm going to do my best to make not a contrived benchmark, but they always are. So in your application, you really should be benchmarking this yourself. The code for this is available. You can use the scripts that I've used, and they're available. I'm going to benchmark it up to 3,000 callables. The callables are each going to be based with a random number of arguments. They're going to have a random callable type, which means it could be a lambda or a class or a field function. It could have bound data members. It could have captures, all sorts of things. The body of all these is also going to be different. And this is important because if they're all the same, we might get different optimizations, and we might get different. No, I won't go into that. Yeah. I'm going to benchmark the code size just using nm with some filtering. The scripts basically use nm, just filter the result. And this is going to be done for every generated source file. So we're going to compile our generated source and use nm to get our code size. And what we end up is this. It's dramatic. Without type erasure, we've got this linear expansion of code size. And this basically continues. This is without optimization, but the conclusion here will not change. I've run this with optimization, and it also doesn't change across compilers, across at least GCC and Clang. The overhead of standard function scales better than no type erasure. So you actually may get a code size advantage by using extra code from the standard library. But it's still significantly more. It has to deal with things like small function optimization. And these extra facilities of standard function result in a poorer code size scaling. Standard function ref is just a couple pointers. So it scales excellently. It looks flat there, but it's actually not. It goes up very gradually. If we were to benchmark compile time, I'm going to use CMake's rule launch target. We can change how CMake invokes the compiler. This is equivalent to using the Unix time utility to run some executable, return the time. Couldn't do that though, got to store the result. I used a Python script. You can get that from the Git repo. And this is what we get. Again, fewer symbols means less compile time. Without type erasure, our compile time is kind of getting out of hand here. To make this graph, it takes like half an hour or something. It's quite bad. Standard function helps heaps. Standard function helps a lot, but standard function has overhead. Standard function will slow down your code. Standard function ref, on the other hand, it's extremely light. It doesn't instantiate as many symbols, it doesn't instantiate as many definitions, and we end up with a much better compile time scaling as well. What about runtime? You know, it must be worse, right? No. Why is it better? It performs better than nothing. Yeah? Yeah, that's going to be part of it. Instruction cache, and if you have branches, perhaps you're using your branch predictor better. You may also you may also make cloning easier for compilation, which is an optimization. But it scales better. It scales better for runtime in this case. I'm going to put a lot of caveats on this. You should run this on your own code, because you're going to have different numbers of branches. The body of your functions is going to have a different size, which is going to change the relative size of your function to the cost of your function to the cost of the type erasure. The bigger that ratio, the better this is. And the body of these functions is like kind of medium-sized, like a few lines with a reasonably large expression. So when we can use this, we should. We should use this over standard function when we can. We should be aware of when we have, when we can't use it. We should be kind to our users of our libraries. We should be kind to our future selves with our APIs. Yeah. Consider replacing some of your templates in your APIs. You can be more expressive using standard function ref or these function wrappers. If you would like to get the slides, they're available here. You can also get the code that extracted the code size, compile time, the generated code, and all these different aspects. Run these on your own projects, because looking at benchmarks like this is roughly useless. But it can give you a rule of thumb. It can give you an indication that you may get really great performance gains, really great compile time improvements with standard function ref. There are some available implementations. These slides, the benchmark, were based on Cybrand's one here, mainly because it's been used several times by other presentations. I think a more up-to-date presentation is the one at the bottom here, the non-type functional repo. So I've tried that one out as well. It looks quite good. Tomorrow, this presentation is largely about type erasure and the benefits of it. This is a type erasing function wrapper. Tomorrow, Fedor will be talking about type erasure more, so if you want to know more about that, attend that talk. Does anyone have any questions? Yeah?
Yeah. I don't know how much you've inspected the generated code from this, but I'm curious to see, is the compiler smart enough to sometimes inline through a std function ref?
Yeah, it is.
Okay.
Yeah. And Vittorio showed this in one of his presentations as well. I omitted it thinking it was I should refer to that as well. Actually, I'll add it to the slides. But yeah, it inlines quite well. It's quite visible. And when you use those non-type template parameters, you can potentially get just a single indirection instead of a double indirection. So it's really great. Yeah. Does that answer?
Yeah, that's very cool. Thank you.
Yeah. Any further questions? Great. Thank you, everyone.